So what are the important properties of alcohols? Well, many small alcohols have a lot of similarities to water because the dominant feature of them is the OH group. But other than that, what we mainly focus on is the OH on an alcohol is both weakly basic as well as weakly acidic. So it's one of those cases that it can do both, but it's not particularly good at either one. But under the right conditions, the addition of a strong enough acid will enable us to protonate it. And we've already seen that, that ability before when we talked about leaving groups. You recall that the protonated alcohol is actually a fairly good leaving group. Likewise, if we add a strong enough base, and that's usually going to have to be something stronger than sodium hydroxide, so it could be NaH, for example, we can form an alkoxide anion. And these alkoxides, like methoxide, ethoxide, and so on, are both strong bases as well as good nucleophiles. But any of these effects is largely based on what groups are attached to the alcohol. And we can see some of those by looking at some specific examples with pKa's. So methanol, for example, which would be our simplest alcohol that we have, has a pKa of 15.54. Now we can influence based on adding electron donating or electron withdrawing groups, as we've seen in the past. So for example, we could put some fluorines on there, or we could put extra methyl groups. Now we've seen before that if we put electron withdrawing groups on, which this example has 3 fluorines on, those will generally help stabilize the conjugate base. I mean, we have a stronger acid. In this case, more than 1,000 times stronger than methanol. But if we add an electron donating group, such as a bunch of carbons, as we have here in this bottom example, electron donating groups destabilize the conjugate base and make for a worse acid. And again, we can see replacing those 3 hydrogens on methanol with extra methyl groups again increases the acidity by a factor of close to 1,000. Now, one spot where alcohols can be a lot more acidic is when we deal with a class of molecules, specifically aromatic ones. And aromatic alcohols are known as phenols. Now, the simplest phenol, which is just the one with the aromatic ring unsubstituted, is actually known as phenol. But anything that's substituted is referred to as basically refers to the phenol as its own functional group. But phenol, especially compared to methanol, you recall, was a pKa of about 15.5. Phenol, on the other hand, has a pKa of 9.89. Why is it so much more acidic? Well, if you consider the conjugate base of phenol, we have an O- attached. and to an aromatic ring. And the result is that that aromatic ring is able, through resonance, to help stabilize that negative charge. And we could continue moving this charge around the aromatic ring. But the result would be the same. We'd continue to show the extra stabilization based on resonance that makes it a stronger acid. From there, we could continue adding groups to the aromatic ring that could have an even bigger effect, or lessen the effect. So two such examples would be the addition of a nitro group. Nitro groups are strongly electron withdrawing and will make this an even better acid. Or an amine. And an amine is one of those interesting examples because by induction, by electronegativity, amines are electron withdrawing. They're more electronegative than carbon or hydrogen. But by resonance, especially being attached to an aromatic ring, the nitrogen on that amine has this lone pair that is electron donating. As we've learned and talked about many times in the past, in general, resonance is a stronger effect than induction. And so the resonance, or the electron donating effect, ends up being the dominant effect here. And so putting the nitro group gave us a better acid, but putting the donating group gives us a worse acid. Now, we can see at 10.46, that's still quite a bit more acidic than when we didn't have the aromatic ring at all. But not nearly as acidic as nothing or having a withdrawing group.